My name is Soren Tornoe, and I'm an electrical and computer engineering PhD student at the University of California, Santa Cruz. The topic I'll be covering today is a brief overview of my research on thin film atomic layer deposition of aluminum fluoride. So, why aluminum fluoride? Well, compared to more traditionally used aluminum oxide, aluminum fluoride protective coatings provide better chemical stability in corrosive environments, remain stable through continuous thermal cycling, and offer exceptional transmittance in the far ultraviolet range. Plus, since fluorine is the most electronegative element, is expected to be capable of depositing on chemically inert surfaces of 2D materials like molybdenum disulfide. This brings us to our method of producing these thin films, atomic layer deposition, or ALD. ALD is a chemical vacuum deposition technique that allows for exceptional conformal coatings and precise control over film thickness. My work focuses on scaling up ALD from typical wafer size to meter size depositions, where variables like gas flow have a large impact on the film growth. In order to keep an even coating across the substrate, the gas is introduced at the center of the sample and pulled to the edges by the vacuum system. This can be seen in the rightmost figures where we have simulations of gas flow in both a wafer and meter scale system. One key detail to note is that to maintain laminar flow, we had to increase the gas velocity in our larger chamber by quite a bit. The first part of this project was depositing aluminum fluoride using our meter scale ALD system. What's interesting is that we initially see the meter scale system has a higher deposition per cycle at lower temperatures compared to the wafer scale system. This, however, drops drastically as temperatures increase and will actually begin to etch away the sample surface as temperature is further increased. The right shows the results of our deposition at 75 degrees C, or roughly our ideal spot, along 3 points in line with the gas inlet and vacuum outlet of our chamber. At position 3, the gas inlet, we found the deposition was 34% higher than the rest of the chamber, but otherwise led to an even coating across the sample. Looking at the refractive index, we found it to be right where we'd hoped it to be at 1.38, with only minor variability between the three chamber regions. So with deposition proved successful, we move on to the bulk of what I'm working on right now, which is depositing aluminum fluoride on monolayer MOS2. Now, MOS2 has many interesting applications, be it as a field effect transistor, memory device, or photodetector, most of which, however, require a dielectric top coating, but this can be difficult to control at desired quality since 2D materials lack the reactive chemistry required for deposition. That said, our preliminary results indicate that aluminum fluoride is capable of depositing on 2D materials. Looking at the Raman spectroscopy results, the peak spacing between cycle 0 and cycle 5 shows a drastic reduction, which is likely brought on by the tensile stress from the growing aluminum fluoride film on top. The A1G, or the out-of-plane Raman peak, shows an initial decrease in intensity consistent with deposition, while the following increase in intensity as well as the instability in the E2G peak is still under investigation. I'd like to thank the ARCS Foundation for funding my research this year.